Have you ever wondered why time only moves forward and not backward? An intriguing question, isn't it? This is the enigma of time, a fundamental aspect of our universe. It's an elusive concept that keeps us all in its unending flow, a constant that we often take for granted. But what if I told you that time isn't as straightforward as it seems? From the ancient philosophers to the modern scientists, many have pondered about the nature of time. Some theories propose that time is absolute, a steady stream that never wavers. Others suggest time as relative, differing based on where you are and how fast you're moving. And then there's the quantum perspective, where time can take on a whole new dimension. These varied theories, each with their own merits and mysteries, make the concept of time a truly fascinating topic to delve into. So, buckle up as we journey through the intricacies of time. Ever heard of Einstein's theory of relativity? Yes? No? Either way, let's dive into it. Delving into the heart of Albert Einstein's theory of relativity, we encounter a mind-bending concept known as time dilation. This isn't about your watch running slow because you dropped it. No, it's an actual change in the pace of time itself, dictated by two significant factors: speed and gravity. Let's imagine you're on a spaceship zooming close to the speed of light. Back on Earth, your best friend is timing your trip. You might feel like the journey took a few hours, but your friend swears it took years. This isn't a case of a forgetful friend. It's time dilation in action. As you approach light speed, time slows down. Relative to those not moving as quickly, it's like the universe hits the slow motion button, but only for you. Now, let's add gravity to the mix. The stronger the gravitational field, the slower time passes. Imagine a clock at the top of a skyscraper and another at street level. The clock higher up, further from the Earth's gravitational pull, will tick faster than its lower counterpart. Bizarre as it sounds, these aren't theoretical musings of a mad scientist. They're experimentally confirmed phenomena. The global positioning system, for instance, has to correct for these time discrepancies to keep accurate track of time. But here's where it gets really interesting. These principles suggest that if you could move fast enough or find a strong enough gravitational field, you could, in theory, leap forward in time. Now, don't get too excited. We're talking about speeds near light speed or black holes. Not exactly tourist-friendly destinations, but still, the implications are staggering. So, in theory, time travel is possible, but only if you're planning to go to the future. Let's take a quantum leap and see what the quantum world has to say about time. In the realm of quantum physics, our conventional understanding of time gets turned on its head. Unlike the linear, one-way street of time in our everyday lives, the quantum world sees time as more of a free-for-all. You see, in classical physics, the concept of time is absolute, ticking away consistently and immutably. It's like a relentless metronome, never faltering, never changing its beat. But quantum physics, the rule-bending maverick of scientific fields, takes a different view. It proposes that time is not absolute, not a constant tick-tock in the background of the universe. Instead, quantum physics suggests that time can be flexible. It can stretch and squeeze, dancing to the tune of quantum particles. And here's where it gets really mind-bending. In the quantum realm, time can go in any direction. Yes, you heard that right. Time can move forward, it can stand still, and it can even move backward. This idea is wrapped up in the concept of time symmetry, a cornerstone of quantum physics. Time symmetry means that the laws of physics are the same whether time is moving forward or backward. In other words, if you were to watch a film of quantum particles interacting and then watched it in reverse, you wouldn't be able to tell the difference. But how can this be? How can time possibly move backward? Well, it's all down to the strange and wonderful world of quantum mechanics. You see, quantum particles don't follow the same rules as the larger objects we're familiar with. They can exist in multiple places at the same time. They can teleport through barriers, and they can affect each other instantaneously over vast distances. This concept of time in quantum physics challenges our everyday understanding of the world around us. But remember, these are the rules of the quantum realm, a world far removed from our daily experiences. In the quantum world, time doesn't seem to care about moving forward or backward. But if time can move in any direction, why does our everyday experience tell us otherwise? Let's dive into the concept of the arrow of time, an idea that has fascinated scientists for centuries. You see, when we talk about time, we often imagine it as an arrow flying unerringly in one direction, forward. This is our daily reality. Our past is set in stone, our future is yet to be written, and we're continually moving from the former to the latter. But what's the science behind this one-way journey? Enter the second law of thermodynamics. This law states that in an isolated system, entropy or disorder always increases over time. Think of a hot cup of coffee sitting on your desk. Given enough time, it cools down, right? That's because the heat energy in the coffee is spreading out, increasing the overall disorder of the system. This is a one-way process. You'll never see your coffee spontaneously heat up again. This increase in entropy gives time its directionality, its arrow. It's why we remember the past but not the future, why we grow older and not younger. We are, in essence, surfing on a wave of increasing entropy carried along by the thermodynamic tide. But here's the kicker. The laws of physics, as we currently understand them, don't require a specific direction for time. They work just as well whether time is moving forwards or backwards. It's only the second law of thermodynamics that introduces this bias, this arrow of time. And yet, there's still so much we don't understand. Why did the universe start in a low entropy state, allowing for the increase that drives the arrow of time? And could there be places in the universe where entropy decreases, effectively reversing the arrow of time? These questions continue to challenge and inspire scientists, pushing the boundaries of our understanding. So the reason we can't go back in time might just be because of our morning coffee getting cold. Our everyday experiences, it seems, are intimately tied to some of the most profound questions in physics. Isn't that a thought to savor over your next cup of joe? But what about our perception of time? Is it real or just an illusion? This is where we delve into the philosophy of time perception. Our perception of time is a fascinating subject that has captivated thinkers for centuries. It's an intricate dance between the physical world and our human minds. You see, time as we know it doesn't tick away in the neat, uniform way we might imagine. Instead, it's a subjective experience that can stretch and shrink based on a multitude of factors. Consider this. When you're engrossed in an activity, perhaps reading a riveting book or playing an intense game, time seems to fly. But when you're waiting for the kettle to boil or sitting through a dull meeting, each second can feel like an eternity. This is known as time dilation, a psychological phenomenon where our perception of time expands or contracts based on our level of attention or emotional state. Furthermore, our memory also plays a crucial role in shaping our sense of time. When we recall a memory packed with detail and novelty, it seems to have lasted longer than a mundane, routine day, even if both spanned the same amount of hours. This is why vacations or new experiences can feel so expansive, while our daily routines seem to blur into a swift continuum. Age also influences our perception of time. If you've ever wondered why childhood summers seemed to last forever, while adulthood years whirl by, you're not alone. As we age, our perception of time speeds up, largely because we're comparing each moment to the total time we've lived. This is known as the proportionality theory. But perhaps the most fascinating aspect of time perception is its subjectivity. Each of us perceives time in our own unique way, influenced by our emotions, experiences, and even cultures. Time, it seems, is not an objective reality, but a deeply personal construct. So, is our perception of time real? Is it an illusion? Well, it's both. It's a real experience, albeit one that's shaped by our minds and our lives. Our perception of time is as complex and mysterious as time itself. Time, as we've seen, is a complex and intriguing concept. It's something we all experience, yet it remains a profound mystery. In the realm of relativity, time is not a universal constant, but a flexible dimension that can stretch or shrink depending on the speed and gravity. Quantum physics, on the other hand, presents us with a timeless world where particles can exist in multiple states simultaneously. Then there's the arrow of time, pointing unerringly from the past to the future, governed by the laws of thermodynamics and our own perception of time. What we perceive as time's relentless march forward is influenced by our consciousness, our memories, and our anticipation of the future. So, we've journeyed through the fascinating world of time, dipping our toes into science, philosophy, and the human mind. And here's a question for you to ponder. If time travel were possible, where would you go and why? Share your answers in the comments below.